This video is going to discuss about the compiler design unit 3 intermediate code generation. So previously we discussed of that syntax analyzer for construction of the syntax tree. That is going to be the second phase of the compiler. So now we are going to take that syntax tree as an input, and now we are converted that syntax tree component to an intermediate code generation. So now the question is, why we are using this intermediate code generation? The intermediate code generation is very, very important. If it is not, we are doing an intermediate code generation, then we have to use a native compiler. That means the analysis part and synthesis part, both of them, we are going to do that within target mission dependent thing. So if we are they're generating an intermediate code generation, then that independent on the target mission. So that doesn't involve the full native compiler for everything to be executed. So the intermediate code generation makes us an easiest thing to compile the things, or we are not supposed to go for an in-depth and in depth of the compilers. So now we are going to see about the overall how we are going to discuss about the structure. So in here, the main thing we are going to see about is what is about in syntax trees and how we are going to generate a tree address code from it, and what are all the different types and declarations we are going to use it of, and how that expressions are going to be translated to a tree address code, how the control flows are going to be used in the tree address code. So these are all the things we are going to discuss that in this video. So now the thing is, I already explained that the intermediate code is going to be the interface between your front end and your back end of the compiler. So here we are from the parsers, we are having a static checker or whatever it may be to check the code. From that, we are going to have an intermediate code generator now. So this intermediate code generator generates the three address code or info intermediate, whatever it may be, in form of an intermediate code that has to be an input for the code generator. So that is going to be given to an backend. So in this particular one, we are going to see about how the syntax tree is going to be converted to one three address code. So now the thing is, there are various structures of the syntax tree are there. It is better we can create a DAG, or that is directed acyclic graph for any syntax trees. So now for an example, here one example we have proceed here with this is, so how we are going to write an A plus A star B into C plus B into C star D. Since B into C has done the two times, we are not going to done with the two times. Here B into C has to be taken care, and we are going to taken that output for the two places directly. So we are going to see that DAG in detail in the next video. So now the thing is how we are going to generate an tree address code for this one. So how we are going to generate an tree address code for a simple statement, simple expression. So take the same expression of this A plus A into B minus C plus B minus C into C. So the same thing, whatever we are doing in any expression, we are going to give the emphasis for that priority of that. So how the priority will come? First will going to be a parenthesis. Next is going to be a multiplication or the division, and then it is going to be for the addition or the subtraction. So the same thing, now we are going to give an importance of that particular whatever there in the parenthesis, and that too from the left to right. So according to the left to right, we are going to use this one. For example, B minus C is going to be used first, and then we are going to be converted that into one tree address code each and every steps. So now we are going to write the first step as T1 is equal to B minus C. Now you can able to see this B minus C star, that is A into B minus C. So that is going to be done here in T2 equal to A into T1. Then next one is going to be a T3, that is equal to A plus T2. Here we can see it of this A plus this, we are finishing it here. Now we are going to have, and the next one is going to be T1 to D. T1 means you can see it here. We are going to do this one, this step. So for that, we are going to have a B minus C into D, that we are finishing it here. And then we are having an thing of, and then we can have an thing of B minus C into D. So we can finish it here. The last step is going to be, the last step of this is going to be a cumulative of almost all the things. So we are adding this T3 plus T4, and that is going to be given it for a T5. So now we can know what is going to be a three address code. So three address code is nothing but we can have in one operator at the right side of an instruction. So for an example, three address, can you see it here? So now for each and every instruction, whatever we are going to do, here we are using only a T1. Then we are having in three addresses here, T1, B, and C or done it here. So can we have another set of things? What are all the different form address of the instructions? We can use it here. So the different set of instructions we can use it here is going to be that the thing of x is equal to x of y, and another one is going to be x is equal to x operator. This x is equal to y operator is it? That means whatever we are seeing in the last example, x is equal to y plus z, or like that we are whatever we are writing. Or otherwise, if I'm having to write it as an only one operator, that is two address things or that, then I have to write it as an x is equal to op of opy. And if it is going to be an assignment operator, I have to write it as an x is equal to y. Then anything to be passed off, or I have to shift it to it, or I have to jump to it, then I have to go with the go to L. Then if I want to do anything of a loop statement, means I have to write like this: if x is equal to go to L, and if f false, then it's go to L. So like that. That is, if it is a true, then we have to go to this. If it is a false, we have to go to this. Like that, we have to supposed to write. If I'm going to check any operation there, then I have to write here if x relop means relational operator of that. Then if you are checking that x relation operator of y, or go to L. That means take an example of if x greater than y, or if x less than y, whatever it may be. Then if it is going to be a procedure call, means you have to write what is going to be the parameter x, and then you have to call what is the parameter, that is what is the function name, and what is going to be that input to be passed. Then y is equal to call of p comma n. If it is going to be an array, then you have to write as x is equal to y of I, or x of I is equal to y, whatever it may be, it is going to be. If it is going to be any address of that, then we have to use a pointer or address, means you have to write x is equal to ampersand y, x is equal to a star y, and x is equal star x is equal to y. These are all the things we can use it for our three address instruction. We can use it in a three address instruction format. So we are going to have a syntax tree. Now we are supposed to convert that to an three address format. So we can take an one example here with that. So already we discussed on one thing. So now we are having another one thing which of somewhat extension thing. So now we are having a loop with a condition. So here a loop is nothing but while a of I is less than or equal to b, I'm supposed to do with I equal to I plus 1. So I can write it with of any loop statement, while or do while or whatever it may be. So whatever we are going to write, we are supposed to write that in a three address format with an if loop. So we have to start here, write this. So I already told you that we have to write everything as in three address format. So here, so first this is going to be I plus 1. So what I'm writing, we can have in various set with that. So first is see it here, we can use this one. We can have this set of things. So in that way, I'm going to use this one here, T1 equal to I plus 1. So I plus 1, it's over. Now I have to, whatever that the value of I plus 1, that I have to give it to the I. So I'm going to initialize that here. That is, I'm going to equate that here. I assign it that I equal to T1. Now the thing is, now I have to go with an array. So this part over, now I have to concentrate on this particular part. So if this is going to be in part, what I'm supposed to do is I have to execute this one. If it's an array, means I have to take care of an array element. So the array element is somewhat different with that of the main element. So the ordinary element, if it's an array element, means I have to write how much of the data type, data sizes. So if it is an integer or a float or four memory required or 8, whatever it may be, we have to multiply that one here. So in general, we are in default, we are going to do it as a float. So T2 is equal to I into 8. That means for each and everything, I need to allocate 8 memory. So now the next one is T3 is equal to A of T2. So A of T2. So here A of I has to be rewrite as. So for each and everything, how much memory we are going to allocate. Then we have to write what is the A of T2. So this A of I has to be written it here as in T3 here. So now T3 is ready with us. Then we are having in less than b, we can write. So we have to check it out. This is going to be a loop. So this has to be checked, and each and every time that particular set of instruction has to be done. So what is the thing we can do it of? So check it here, which one can we use? So we can use of with this go to L. So see it here, if X, go to L or whatever it may be. So the same thing we are using it here once again. So if T3 is less than B, go to L.